Buddy, let's take your seat if you can. Well, I'm sure you can. Take your seat, please. It's not really a question of can you, but will you? All right. Hush has come over the room. All right, we're going to get started on the next session, which is focused on water quality and groundwater-dependent ecosystems. And our first speaker is Dom DiGiulio, who's a senior research scientist at PSE Healthy Energy, but he's also a visiting scholar at Stanford, and that's where I came across some of the work he's done recently. He's spent a very long time in his career working at EPA, which is one of the key characters in the story of Pavillion, Wyoming. This is the place you'll recall where some people could light their tap water on fire. At least that's what the video showed. This is a oil and gas case. And it gained a lot of attention throughout the West, in part because of that dramatic video, but in part because there are a lot of places in the West that are dealing with oil and gas pressures. Boulder is one of those places. It's a very big issue here. And there's a lot of issues surrounding this, but one of the biggest issues is a pretty fundamental research question, and that is to what degree is the fracking activity threatening groundwater reserves? And so that is a broad enough subject to keep you busy for a half hour.
Hey, Doug, thank you very much. So I was a principal investigator. I retired from EPA in 2014, and I was a PI for the Pavillion site. Lots of politics there. It's the first site where groundwater contamination due to hydraulic fracturing was first documented, and lots of politics. It was a part of a congressional investigation in 2012, and I think that's when it got most of my gray hair. So, okay, so what I really want to do in this presentation is make the case that there's a need for clear, robust state regulatory criteria to protect groundwater during oil and gas development, and then provide an example with the Pavillion field as to why these criteria are necessary. So, but first I want to give a brief overview of why it's necessary to protect brackish groundwater, and then give a very brief overview of upstream, in the oil and gas field, sources of ground contamination. So, if you look at a USGS water budget, almost 1/2 of our water supply comes from groundwater, and there's a growing percent of groundwater being used with irrigation. Because of the decreasing freshwater availability, there is an increased demand for direct use of brackish groundwater and for treated use of brackish groundwater, primarily because of advances in membrane technology. The cost of desalination of brackish groundwater has really come down. The USGS defines brackish groundwater as having between 1,000 and 10,000 milligram per liter of total dissolved solids. In 2010, there were almost 650 desalination plants. And the dark blue circles here are desalination of brackish groundwater, whereas the light blue circles here are desalination of seawater. So brackish groundwater is really the vast majority of desalination. There's been some discussion about the impact of climate change on groundwater resources. This is a really great paper from Roy et al. In Environmental Science and Technology in 2012. And they looked at stresses on water resources. So here, white is low, yellow is moderate, red is high, and brown is extreme. So in 2010, pretty much most of the water stress was in the mid-continent area and the western states. But if you flash forward to 2050, water stress is going to get much worse in the mid-continent area and with the western states, and even moved to the eastern part of the country. This is mostly due to increased evapotranspiration, increased heat, and population change. So quickly, I just want to go into the need why there's really a need to protect fresh and brackish groundwater resources during oil and gas development. And one reason is disposal of oil and gas wastewater into Class II wells. Right now, there's over 1,142 disposal wells where you actually inject wastewater from oil and gas disposal into groundwater aquifers. If you plot these on a map, most of them are in the Rocky Mountain states and in California. So these are fairly arid parts of the country. There's been a number of publications in the past few years looking at literally thousands of spills on these oil and gas fields. So there's I think a recognition that this is actually fairly common. This is something I'm working on right now, actually, the seepage of wastewater from impoundments and pits. There was a 1987 EPA report that identified over 122,000 unlined pits in the country at that time, and it's just gotten worse from there. There's a lot of these pits are being closed, but states like California still allow the disposal of wastewater into these pits. So that's definitely a concern. And let me just jump here to beneficial use. We published a paper last year looking at the beneficial use of wastewater. There's a whole lot of oil and gas wastewater that's being produced because of hydraulic fracturing. And so there's, I guess, increased concern of where this stuff is going because of seismic activity, earthquakes occurring with disposal in Class II wells. There is really a push to dispose of this wastewater in different ways. So we have some basic concerns about the ability to actually detect a lot of the compounds present with unconventional oil and gas. There's been a whole series of papers written in the past 5 to 10 years looking at trying to identify literally thousands of compounds. So the standard EPA analysis is not very good at identifying or detecting and quantifying the vast majority of these compounds. There's also concern that we really don't know the physiochemical and degradation properties of these various compounds, and then we don't know the toxicological properties. And finally, there's very few field studies. Like if you take road spreading, that's been occurring for the past 40 years, and there's only really one study published, and that was published in 1984, looking at the effect of road spreading in brine. And that study actually showed contamination of groundwater. So there's really a lot of work that needs to be done here. And so just moving on, our group at Stanford actually looked at one potential stressor, and that's the vertical distance between hydraulic fracturing and the surface. Worrying about potential propagation of fractures to groundwater resources. And this paper was led by Rob Jackson. About 6% of high volume hydraulic fracturing occurs within 3,000 feet of the surface. I think we probably need to rework this paper and not so much be concerned about distance from the surface, but actually distance to a water resource, because especially with the Rocky Mountain states, the brackish groundwater resources, water resources are fairly deep. And then, okay, today's topic is to talk about injection hydraulic fracturing as a stimulation directly into water resources, directly into brackish resources. So this all starts with having a regulatory, a groundwater protection starts with a clear, robust regulatory definition of protected groundwater. So this is pretty much run by the states, and there is a clear definition that would be under the Safe Drinking Water Act, and that's an underground source of drinking water. And that's defined as water that contains less than 10,000 milligrams per liter of total dissolved solids. But the Energy Policy Act of 2005 basically stated that hydraulic fracturing, that injection during hydraulic fracturing really was not injection. And then, so I have a question. I guess there's a bunch of legal scholars here, and I want to take full advantage of that. Did this exemption just remove the Class II requirements in terms of how you monitor a well, in terms of well integrity and things like that? Or did this actually legalize the degradation of groundwater resources by allowing hydraulic fracturing right into water resources. So I'm hoping that the answer to that question is no, but with my experience thus far, it seems like yes. And so I'm kind of wondering if this exemption, if it's really illegal to dispose and degrade or destroy a groundwater resource. And so I think until this is actually challenged, I think the answer is still probably yes. So at least in theory, or at least I think there's a consensus in principle that this should not be happening. So with API, the primary trade group with the oil and gas industry, they say that surface casing, which is the major way of protecting groundwater resources, should be at least 100 feet below an underground source of drinking water. The Groundwater Protection Council works very closely with the oil and gas industry, and state regulatory agencies also say that hydraulic fracturing should not be occurring in underground sources of drinking water. This was 2009. There are reports in 2014 and 2017, though, have not had this statement. So it's conspicuously absent, actually. The California State Water Resources Control Board also stated in a document looking at monitoring of hydraulic fracturing in groundwater, stated that a standard of 10,000 milligram per liter of TDS is appropriate because it aligns with EPA's underground injection control program and is technically and economically feasible to desalinate water at this level. So I guess most importantly as well is that was a 2015 BLM rule, which said that because of increasing water scarcity and technological improvements in water treatment, it is feasible to protect groundwater at a level of 10,000 part per million. But elections have consequences, and in 2017, this rule was rescinded, stating that it would hinder economic growth. So I was pretty excited when this rule first came out. I thought, okay, at least on tribal and federal lands, we're going to have protection of groundwater resources during hydraulic fracturing, but it's not so clear now. So we published a paper several months ago trying to get some idea of if groundwater resources are being impacted on a wide scale, where is it probably occurring? So we looked at the USGS reduced water database, and we looked at almost 166,000 wells. We found almost 19,000 production wells where the TDS levels were below 10,000 part per million. And so there's 27 oil and gas producing states that produce something like 99% oil and gas production in the country. And if you look at this graph here and you pick out those red dots, which are gas and oil production wells, it really comes down to about 17 states where there's potential hydraulic fracturing into brackish groundwater resources. And as you can see here, most of it here is with the Rocky Mountain states. So in this paper, we asked the question, well, do the definitions of protected groundwater in these states, are they equivalent to an underground source of drinking water? And so the light blue states here are the states that did not contain significant brackish groundwater resources. And then I did kind of a traffic light here, green, yellow, and red, looking at various states and whether their regulations actually were protective of groundwater resources. So the green states here, five states, in their oil and gas regs, they do say that you should be protecting groundwater to the standard of an underground source of drinking water. With the yellow states here, it wasn't so clear. There's not clearly defined terms. Often they use terms like freshwater, which are not clearly defined. In some cases, it just varies where you're at from state to state. There were 3 states here, though, West Virginia, Wyoming, and Montana, that explicitly remove protection of groundwater during oil and gas development. So there's actually language in the regulations that removes protection of groundwater resources. So why is that important? Well, the reason that's important is that if you don't have protection of groundwater resources, then you can legally inject stimulation fluids into these formations that contain water resources. So in 2004, EPA did a study on coalbed methane and found that at most coalbed methane fields throughout the country, hydraulic fracturing was in fact occurring in underground sources of drinking water. So in some of these states that I had highlighted in green, like Oklahoma and Kansas and Utah, it still seems like there's hydraulic fracturing occurring in formations that contain an underground source of drinking water, even though the regulations say that this should be protective of underground sources of drinking water. Then with the yellow states here, like Colorado, there's definitely hydraulic fracturing occurring in underground sources of drinking water, like the, with the Raton Basin and the San Juan Basin. The San Juan Basin was identified in 2004. One of the EPA retrospective studies in 2016 for the national study identified hydraulic fracturing in the underground sources of drinking water with the Raton Basin. So this is why this is important. It is occurring. And so if you listen to politicians talk and actually senior level officials in government, you keep on hearing there's not one documented case of groundwater contamination due to hydraulic fracturing. I think you can only make that statement if you identify groundwater resources, groundwater contamination with people's wells. So it's clearly not the same thing. You can contaminate groundwater, like this schematic from EPA 2004 shows hydraulic fracturing in coal seams and subsequent contamination of groundwater resources, but a person's well here was not affected. So you can have contamination of groundwater resources, you can degrade resources, but not necessarily degrade a person's well. So it's, like I said, it's not the same thing. It took about 10 years, but in February of 2014, EPA finally came out and said that direct injection of these stimulation fluids into a USDW presents an immediate risk to public health. So there was a definitive statement finally in 2014 about that. Then for the national EPA study in 2016, it did the same thing that we did in that paper. They looked at produced water concentrations, and they actually looked at 1,200 samples and concluded that that TDS were less than 10,000 milligram per liter in 73% of the cases. So I think because they looked at states like Colorado and Wyoming and Utah where there's a lot of brackish groundwater resource, so their percentage was a lot higher. So they came up with the conclusion that the overall frequency of this occurrence is relatively low, but it's concentrated in particular parts of the country. So I would totally agree that this practice is likely concentrated in particular parts of the country, certainly the Rocky Mountain states. But I would also conclude that the overall frequency is not known. No one is really conducting research into this topic right now, looking at the frequency of injection of stimulation fluids during hydraulic fracturing into underground sources of drinking water. So I don't think we really know what the frequency is. So let me jump to the Pavillion site. I spent a great deal of time here. So the Pavillion field is in the Wind River Basin. This is just one of many basins in the Rocky Mountain area. Each of these green areas is a basin with lots of oil and gas production. So this is the Wind River Basin. The Pavillion field is in the center of the basin. These dots here are oil and gas wells. So the actual field runs along the western part of the field, runs along a fault. So okay, so here's the field itself. There's at least 180 production wells in this field. The production wells are red, and then these splots here, or these stars, are plugged and abandoned wells. And then these light circles are people's domestic water wells. And this diamond here and these black squares here are these unlined pits. There's 44 unlined pits in the Pavillion field that were used for disposal of diesel fuel-based drilling fluids and production fluids, which would be flowback, produced water, etc. So if you look at the proximity, here's a scale right here. If you look at the proximity of these unlined pits and people's wells, they're pretty darn close. And so that's a problem. And so we're working on a paper right now actually trying to document impact of people's wells as a result of these pits here. But if you live there, you've got this problem essentially that these pits are contaminating near surface groundwater to some unknown depth. And then you have hydraulic fracturing contamination. You have groundwater contamination due to hydraulic fracturing down around 750 feet to 1,000 feet below ground surface. So if you live there, it's kind of like dodging bullets. You know, you're trying to put a well down, and you've got surface contamination, you've got this stuff coming down, and you've got the fracking fluid coming up. So it's, you know, literally between a rock and a hard place. So just quickly, some geology here with the Pavillion field. The source rock is the shale formations, and then these move up to the Wind River and Fort Union formations through fractures and rocks. And at the Pavillion field, the Wind River formation it contains both oil and gas, but contains water resources as well. And that goes from about 0 to 3,000 feet. The Fort Union formation contains oil and gas, but also water resources. And that goes about 3,000 to 6,000 feet below ground surface. So if you wanted to get some idea as to groundwater resources in the Rocky Mountain West or the Mid-Continent area, and you want to get an idea of where the brackish groundwater resources are, where the water resources are, where the oil and gas fields, a good place to start is with this USGS report published last year. It's really a great report. It goes into brackish groundwater resources across the country. So if you look at the Wind River Basin, you got these lower tertiary aquifers that are present there. And from the USGS report, there's two scales here. One's an upper bar scale from 0 to 500 feet. Then there's a lower scale here from 0 to 3,000 feet. But if you look at the research that USGS did, literally 100% of the water there has TDS levels below 10,000 milligram per liter. So all the water there in the Wind River formation, the Fort Union formation, the formations where we're fracking in, is a source of underground source of drinking water. And greater than 95% of that water has TDS levels less than 3,000 part per million. So it's pretty decent water. I mean, you can drink water between, you know, up to 1,000 or 2,000 part per million TDS. It gets kind of salty, and it's hard to drink water over, say, 3,000 part per million, but you can treat this water as well. So we're doing fracking in the water that can be drunk without treatment, plus we're worried about hydraulic fracturing in the water that can be treated at fairly low cost. And so just getting a little deeper into this, the TDS levels based on work from USGS and work that EPA did out there is definitely meets this, you know, the TDS levels are less than 1,000, meets the definition of an underground source of drinking water. And then this is the Wind River formation is widely used throughout the Wind River Basin. It is the primary source of drinking water there. It supplies a town of Pavillion with 5 public wells. And so it is the major formation there where people draw their water. The Fort Union formation is not as widely used, but it still meets the definition of an underground source of drinking water. And as proof of that, an aquifer exemption was granted just northwest of the fields to, you know, essentially dispose of wastewater in that underground source of drinking water. So it all boils down to this. I mean, this argument still is going on in terms of whether these are really sources of drinking water, whether the formation where we're doing hydraulic fracturing is a source of drinking water. One argument is that it's not, because in the state of Wyoming, they have these 6 classes of groundwater. Class 1 is less than 500 part per million of TDS. Class 2, less than 2,000. Class 3, less than 5,000. But they have this Class 5 for hydrocarbon production, which does not have a TDS criterion, where basically you can do oil and gas production and not worry about protecting groundwater. And then there's a Class 6 as well, where you would say, well, the water is really not suitable for use because of excessive TDS levels, but excessive is not defined, or it's so contaminated that you can't really use the water, or it's too deep. So I would say this is a USDW because EPA explicitly said so 3 times. When I worked with EPA, we said so in 2010. EPA Region 8 said so again in 2013, said that not only is the Wind River and Fort Union formations USDW, but hydraulic fracturing did occur in those formations. And in 2016, in a national EPA study, this was the same statement. So I think that's pretty clear. The TDS levels meet the definition of underground sources of drinking water. The definition of a USDW is not dependent on a state water classification system. And then, the presence of natural gas does not invalidate, the presence of an underground source of drinking water. If there's a lot of oil and gas there, especially oil, and the groundwater meets the definition of a USDW prior to the exemption with the 2005 EPA Act, you would have to apply for an aquifer exemption to do work in that area. Class 5 does not have a TDS criterion. At the Pavillion site, hydraulic fracturing occurred in Class 1, 2, and 3 water. And so in this case, you would have Class 5 water the water is Class 5 at the same time as Class 1, 2, and 3, which really doesn't make a whole lot of sense to me. Again, for Class 6, there's no criterion for TDS. And we want to say the water is so contaminated, I would say it wasn't contaminated prior to hydraulic fracturing. And then finally, the water certainly is not too deep because there's water wells in Wyoming that go down about 3,000 feet. And because hydraulic fracturing at the Pavillion site was very shallow. So if you look at the ground surface here, and this is approximate depth in meters below ground surface, this is the deepest domestic water well use in that area, around 300 meters or about 1,000 feet below ground surface. You had hydraulic fracturing occurring nearly at the same level there as people were using the water, and as the stimulation was occurring as shallow as 700 feet. So you can't really argue it's too deep when you're doing fracking at the same depth. So there's, I think without the exemption of the Safe Drinking Water Act, there'd be a lot more thought about, depths of fracking, depths that we need, that groundwater needs to be exempted from protection. But clearly this is a situation where things got way too shallow. And so probably don't have time for this. I included some additional slides, but Rob Jackson and I, in a paper in Environmental Science and Technology in 2016, took this a step further, where we not only said that there was fracking occurring in the underground source of drinking water at the Pavillion site, but it actually had impacted the water resources there. So at the Pavillion site, there is almost 11,000 million gallons of stimulation fluids injected directly in the formations, meeting the definition of an underground source of drinking water. So I spent 31 years with the EPA in the CERCLA program, the Superfund program. If I would have told you that I could inject pollutants in the groundwater and not expect contamination, people would have laughed at me, and I would have just been ashamed and just walked out of the room. But in this kind of field, you can, I guess, have a straight face. So I can inject 11 million gallons of stimulation fluids and not expect contamination. But we looked into 5 lines of reasoning here as to why impact would occur, and one was injection of stimulation fluids right into water-bearing sandstone units. So there are several cases where undiluted diesel fuel was actually injected right into water-bearing sandstone lenses that would bear water that would meet the definition of an underground source of drinking water. We looked at propagation of fractures and leak off of stimulation fluids into water-bearing sandstone units. Then this is not shale where there could be a large vertical separation. The separation distance here is very close. We looked at pressure buildup during hydraulic fracturing, and in many cases it was orders of magnitude greater in terms of that hydraulic head that would push stimulation fluids upward than you would get from drawdown. Then loss of zonal isolation in production wells. A lot of these production wells had lots of problems, whether there was parting of the well casing or lack of cement or injection of stimulation fluids really at the base of the cement where there's not a whole lot of cement above where you were injecting the frac fluids to prevent that from moving upward. And then finally, we installed 2 monitoring wells out there in that field at 750 feet below ground surface and 1,000 feet below ground surface. We found organic contaminants that were associated with hydraulic fracturing. So if you put all these together, and the fact that you injected this much, I think it's pretty compelling that it's the first documented case where you did contaminate groundwater resources due to hydraulic fracturing. So in conclusion, if you've been sleeping, I guess the thing I really want to point out here is that we need these criteria established with an underground source of drinking water under the Safe Drinking Water Act to protect groundwater resources because right now the state criteria are fairly ambiguous. They're not consistent. The report that EPA had published in 2004 showed that hydraulic fracturing was occurring in underground sources of drinking water, and following the work that we did Pavillion, again, at least with tight gas formations as well as coal bed methane, had documented that this is in fact occurring. And I will stop there. Thank you. Questions, anybody? Yeah.
I know one problem in Colorado determining contamination well is that there is no requirement for testing
I think the recent Wyoming rules now require baseline testing. I can't remember, I think at least 5 wells. I don't know what Colorado does. I know Montana was considering that. We had submitted some comments with the state of Montana on their baseline testing, but I'm not sure what the regulations are in New Mexico or Colorado or the rest of the Rocky Mountain states, but Wyoming, I think in 2014, actually required some baseline testing. I kind of really wanted one of the attorneys to stand up and correct me when I said something about the underground sources of drinking water and is it legal? Is there any attorney here, a legal scholar, that would respond to that? I'm really trying to take advantage of the expertise in this room. I kind of, yeah.
You were correct, but the Energy Policy Act took hydraulic fracturing, unless it contains diesel, out of the definition of injection. So therefore, it's not, it doesn't fall under the Safe Drinking Water Act because it is not an injection.
But is it currently legal to actually inject, to destroy a groundwater resources?
Congress,
is that legal right now, at least on private land?
it is not regulated under the Safe Drinking Water Act. So a state could potentially have legislation or laws about it, but it is exempted under the Safe Drinking
That was
Water
probably a yes?
Act. Yes.
Okay.
Dominic, let me add a little clarification to what Lucida said. The 10,000 and that requirement only relates to the underground injection control program. Doesn't relate or is not applicable to anything else.
Right.
So it only is UIC. UIC is a waste disposal program.
Right.
So what the law says is if you want to dispose of waste fluids from oil and gas into a USDW, 10,000 or less, you got to get a permit or an exemption.
Right.
But if you are putting drilling fluids, development fluids, that's not waste disposal. That is not subject to UIC.
Right.
Therefore, the answer is yes, you can contaminate groundwater resources less than 10,000 TDS with oil and gas. You can absolutely do that, and it happens. Wyoming tries to get around it with this class 5, 6 stuff. And then one other comment, the background stuff, you're right, in Wyoming did that, but don't fool yourself. They only require testing of 5 wells that are nearby domestic wells, which are 100 feet deep and nowhere's near where the contamination occurs. So that just doesn't work.
Right.
So anyway.
I agree. Okay, thank you. Yeah. Turn this off.
We did a, you're killing me. No. I'm gonna keep us on schedule. I'm gonna move forward. We did an entire conference on this subject a couple of years ago, and so I'm very aware that we could easily spend 2 days talking about this, if not more. So, but I'm gonna try to keep us on schedule this morning. So moving forward is we got Dave Kramer, who's a hydrogeologist at UNLV, and Dave has worked all over the world. But it's the West, I think, that has a special place in his heart. And I know one of the places that has a special place in his heart is the Grand Canyon and downstream of the Grand Canyon. He likes to drop his kayak in just downstream of Hoover Dam. And one of these days I'm going to show up at your house and take you up on your offer to go rafting down the river there. But of course, that's also a part of the world where there's a lot of pressure to do uranium mining, and Dave is very knowledgeable about the legacy of past uranium mining in the area, so he's certainly very engaged in the current proposals to do more of that. So with that, Dave?
Thank you. Can I be heard? I dropped my microphone here, and can I clearly be heard here, or should I adjust it? Is that pretty good? Okay. Well, thank you. I want to thank the organizers and the sponsors of this gathering. It's been great, and I want to thank Doug in particular for inviting me to speak. The title I was given is A New Era in Uranium Mining in the Colorado Plateau. It turns out that uranium mining is very subject to the price of uranium, which plummeted in the 1980s, and many mines were shuttered. They went on standby mode, which means they put a fence around them, and nobody was there, and the piles of waste blew into the surrounding area. Prices began to come up about a little over 10 years ago, and so perhaps a better title for this would be, will an old era uranium mining on the Colorado Plateau come back, and will it come back prematurely? I'm going to center on a case study in the Grand Canyon, and I'm going to do this for 3 reasons. One, it's an interesting political and legal squabble right now. The second is that it highlights very endangered and vulnerable ecosystems, that is, small springs, which are ignored by a lot of our laws. And the third reason is it gets an opportunity for me to show you a lot of pretty pictures. So another title might be, will the springs of the Grand Canyon dry up or be contaminated? And so are these too many titles for one talk? I'd like to start off with acknowledgments. I'm going to show a little data later on in the talk, and the data is gathered by people from the National Park Service and the people who have organized this conference who've given me an opportunity to present. Graduate students who have collected a lot of the data and undergraduates who have helped out as well. Here's one of them, Jim Fitzgerald, long hikes in backcountry and slogs to some of these springs. Kim Zukowski here working late at night filtering samples. And also many graduate students, boatmen, Park Service people, USGS people. Abe Springer is from Northern Arizona University. This is Horn Creek, where my research group was the first one to find high uranium in springs of the Grand Canyon about 25 years ago. And so it's a very beautiful side canyon to the Grand Canyon. So my talk outline is I'll give you an introduction to uranium mining on the plateau, then I'll go into Grand Canyon issues, and a moratorium on mining is actually in place right now, and it's vulnerable. Uranium mining, and orphan uranium mine, is an example of how contamination might spread. I'll talk about potential contamination and aquifer disruption, and then finally the future. First of all, the uranium resources in the United States are highly in the Colorado Plateau area. You can see here that it's highly centralized in where we live and where we work. These are locations of mines with uranium from EPA data. And again, you can see very, very strongly correlated to the western United States. But it's had a turbulent history, and a lot of Native American and First Nations interests are tied up in this. Those of you who don't know about the 1979 spill in Church Rock from the Grants Mineral Belt, a tailings pond broke, and you can see up here where the tailings broke. And uranium-laden water, it's been described as the biggest radioactive release in the United States history, flowed down wash over 80 miles from New Mexico into Arizona to the Navajo Reservation. And the Navajos protest every year uranium spills. It's a turbulent issue, particularly with the tribe. So these are some protests here. The one on the upper right actually is kind of interesting. Mike Wireman and I worked in northwestern Nebraska on in situ uranium leach mining. And we were testifying for the federal judges for the Nuclear Regulatory Commission, and outside there was that upper protest there going on At the same time, we were representing the tribes and the surrounding people who lived around this in situ uranium mine, leaching mine. For those of you who don't know, that means that instead of digging a hole in the ground, you inject water into the ground that has a mobilizing agent for uranium called a lixiviant. It grabs the uranium and it becomes what they call a pregnant solution, which is pumped back up, and then the uranium is extracted without mining. But it has potential problems. So this is Arizona down at the bottom here, New Mexico. These are some of the tribal areas, and the red dots on this is where the uranium in wells is 5 times the background. Over $110 million was put in this area to clean it up, but you can see that it's also a Native American sort of justice thing that's involved here as well. So let's talk about the Grand Canyon. If you're interested, there's a beautiful film called Too Precious to Mine that made its debut, the Grand Canyon Trust, February in the Flagstaff Mountain Film Festival. It's a beautiful film, but it talks not only about a little bit about the hydrology, but more about the Native American concerns and also the economics of the region. It turns out that in northern Arizona, the economics is not driven by mining, it's driven by recreation. So Grand Canyon, a lot of you know about it. It's a large area. It has over 6 million visitors a year. Its elevation has great range from the rim down to the river. It has a hydrogeology that's interesting, and I won't be able to get into much of it here. It's not known as a cave park, but recently we found a cave that goes 20 miles of passage. So it's kind of interesting, and it's a World Heritage Site. So Theodore Roosevelt and many other Native Americans and other people said, leave it as it is, you can only mar it. So this is the Silver Grotto in the Grand Canyon, and if you run really fast around here, you can run without falling in the water, but you got to run fast. My own perspective on mining in the Grand Canyon comes from a different quote, and that's from my scoutmaster who said, Dave, leave your campsite cleaner than you found it. So we all know where the Grand Canyon is. It's in Arizona, and let's zoom in here, and there it is there. And there's the Grand Canyon, there's the park, that's the north rim and the south rim down below. The Kaibab National Forest, about 1,000 feet higher on the north rim than the south rim. This is Havasu Canyon over in this area here. Very, very beautiful water. Those of you who have been there know that. Over in the Little Colorado River over here is where the Little Colorado River comes in. It's a sacred site to many of the local tribes, the Hopi, the Navajo, and others. When it flows big time. It's a beautiful side canyon. Down south here is the town of Tusayan, about 10 miles south. It's got wells that go down 2,500 feet and pump from the same aquifer system that feeds most of the major springs. And the number of wells keep growing. So the groundwater issues at the Grand Canyon then are spring and wildlife habitats. They're very, very important, and some of them are immobile. They can't go spring to spring. The California condor is the largest wingspan bird in North America, and that's been reintroduced there. Importantly, the Native American religious traditions are associated with the Grand Canyon. And I don't have time to emphasize this enough, but there's a certain spirituality associated with these springs that's very, very important to protect. And then lastly, I'll talk about the uranium mining history. There was a uranium mine right on the rim of the Grand Canyon, and this uranium mine was called the Lost Orphan Uranium Mine. It was a tourist attraction with headworks right up on the rim, about a mile west of Grand Canyon Village on the south rim. And we found high uranium. This is a picture where the miner's going down to the mine to work the uranium. We found high uranium in a spring directly below that in Horn Creek about 25 years ago. So the Park Service said, well, maybe we should measure to see if there's any radioactivity up at the surface. And at this tourist attraction, they found it was hot. And so they put up a fence around it, they dug up the dirt, they knocked down their headworks here and they put down geotextiles, and it is a Superfund site in the Grand Canyon. So I'm going to give you a four-part timeline just to bring you in line of what's been happening there. In 2006, uranium prices began to rise. There were thousands of claims for uranium mining all over the Grand Canyon area. A Canadian-owned company reopened a White Mesa mill in Blanding, Utah, and began processing uranium. I should mention, most mining companies who want to mine in this area are multinationals that are not primarily from the United States. They're from Canada, Russia, and they sell their uranium to non-U.S. sources, usually France and Israel and other places. The U.S. Forest Service began permitting exploratory drilling without requiring environmental assessment, and the Bureau of Land Management moved to allow uranium mines that were abandoned by previous owners to reopen without updating their environmental regulations. Part two here, in 2007, the Kaibab National Forest approved mining. Kaibab is right near the Grand Canyon. The Coconino County Board of Supervisors from Flagstaff area, just south of the Grand Canyon, voted unanimously opposing uranium development. Again, the economy of the region is really a broad coalition of environmental and recreational uses. In 2008, the Center for Biological Diversity, the Grand Canyon Trust, and Sierra Club sent a letter requesting that the National Forest remove approval for up to 39 mines, and they got a temporary restraining order, which was granted. Citing widespread public opposition was one of their things, and a flawed environmental review was another criterion. Congressman Raul Gravalda from Arizona introduced the Grand Canyon Watersheds Protection Act. A bunch of people, including myself, testified before Congress on this act. The newspapers said there's a Cold War going on here. The Metropolitan Water District of Southern California and the SNWA from Nevada, they all said that they were worried about uranium mining upstream of their water sources. The U.S. House of Representatives Committee on Natural Resources voted in favor of a resolution requiring the Secretary to withdraw lands. This was under Bush. They refused to do it, and the short of this part here is that it wasn't implemented. The opposition to this vote was not implemented until the Obama administration took office. And lastly, a British mining company pushed ahead to restart a uranium mine in the Grand Canyon area. This is the important one here. Interior Secretary Salazar put a 20-year moratorium on uranium mining, grandfathering in about 5 mines that had operated before in the Grand Canyon area, but no new mines, and that gave time for people to review the environmental situation. The USGS did a lot of work, and they refuted uranium industry claims that the Grand Canyon withdrawal is just 40% of the uranium for the U.S. It's only 1.5%, but it's very pure uranium, which makes it attractive. And now there's lawsuits going on. They're trying to get that withdrawal or that moratorium on new mines withdrawn. Okay, Grand Canyon Springs are beautiful. There's Elves Chasm. That person's midair there, jumping down. Recharge in the area is very localized sometimes. But it's canyon by canyon. You can have flash floods. They can wash things on the surface away. I think Lenny Konikow mentioned that the upper Colorado River Basin, over half of the flow is fed by base flow, which is groundwater. So very localized recharge, and what that means is you have very beautiful runoff events. It's kind of interesting to be boating down the Grand Canyon when this happens. Those are not normally there, those waterfalls. So there's one of my graduate students. She's outstanding in her field. They're hotspots of biodiversity. They're a lot of endangered species. The Endangered Species Act is really the only hammer we have legally to protect some of these springs. The location of less than 10% of springs in the West are known according to the Spring Stewardship Institute. As they find new springs, they're not mapped. People don't know where they are. This is not from the Grand Canyon, but it illustrates something. This is Bonanza Spring, which is in the middle of the Mojave Desert. And the point I want to make here is the biological diversity of a spring environment is orders and orders and orders of magnitude more than just 10 feet away or 10 meters away. And so these are really biological hotspots. This is Havasu Canyon again. There's a Native American tribe that lives down in the Grand Canyon here. And some hydrologists feel that this spring or set of springs is recharged by an area bigger than 2 times the state of Delaware. These are windows to aquifers. I want to point out that a lot of our laws that we've been talking about don't really apply, you know. Navigable waters, in-stream flow, where's the stream, you know? But yet these are areas that attract all sorts of wildlife, and they're very, very vulnerable to small changes in water table and things of that sort. This is Pumpkin Spring here. It's kind of shaped like a pumpkin. You can't really see it too well. Very high in arsenic. But yeah, there's people sitting in it. It's very high in arsenic, but just don't drink it. But springs are very vulnerable to slight changes in water table. And this could be due to groundwater exploitation or climate change. And it can dry up springs and creeks, and this is particularly true in the Grand Canyon. These mines also use water for their operations. So in a study recently, not yet published, but in the publishing process, it's a PhD dissertation out of Northern Arizona University. Dave Sinclair, working with Abe Springer, said that in their study of 350 plus springs, they're less than 0.01% of the landscape was covered by these springs, but they supported over 44% of the taxa and a lot of native taxa as well. So I'm not going to talk about science much in the end of the talk here, but there's a lot of interesting things about doing science in the field. In the winter when you're sampling, the snow can blow sideways, and you sleep with the water bottles in your sleeping bag so they don't freeze, which makes it interesting. In the summer, you know, you're hiking out with 110-degree temperatures with many, many pounds of water you can't drink on your back. But I'm not going to talk too much about the, you know, conduits and the fractures and faults into the Grand Canyon or the modeling. Well, not a lot. I'll talk a little bit about it. The groundwater is invisible to many decision makers. An example of the invisibility is a recent study we're still doing. Right now we have over 6,000, but at this time it was over 4,000 sampling events in the Grand Canyon. We looked historically from the 1950s all the way to the present for everybody who went out and sampled a spring and or a creek. And we found the samples here, about 75 springs, a couple of wells in the area. And we evaluated for the EPA maximum contaminant levels. That's the drinking water standard. And we did it for a whole bunch of chemicals, which I can't show you all of them. But I want to point out, first of all, that most of the sampling events of these springs were done over 15 years ago. So not only are these springs invisible from sight from people, but water quality-wise, they're invisible. So this is arsenic. And in arsenic in the Grand Canyon, 87% of the time it wasn't even analyzed when somebody visited a spring for sampling. When it was sampled, there were non-detects about 11% of the time. There was some detection, though, 88% of the time. And when it was sampled and when it was detected, over half of the time it was over drinking water standards. I found that to be very, very interesting. So here's a high arsenic content naturally in these spring waters that nobody really recognized. And so just those of you who love and know the Grand Canyon, here's some of the springs that were high in arsenic. Here's some of the creeks that were high in arsenic. And I know some of you are Grand Canyon River rats, and you probably know these places. And okay, so here's some data, and it's a lot of data in here that I don't have time to explain or for you to look at, but I'm getting near the end here. I just want to explain that this is Horn Creek below Orphan Uranium Mine, 92 and 27 for uranium, 234 and 238. The standard is 30 micrograms per liter, so this is well over standard, and that's what got things going. Just to explain a little bit of where the uranium mining will occur. First, this is what's called the R aquifer. It's the red wall, Temple Butte, and Mauve limestones. It's underlain by shale, which is like a dinner plate, so the water percolates down and then is shoved sideways to the wall of the canyon. There's also what we call a perched aquifer, and that's the C aquifer up above. It's underlain by the Hermit shale. Think of it as sort of like a dinner plate. There's the Hermit shale. There's the Coconino sandstone, which is permeable above it. And that little icicle-looking thing is travertine, indicating that in the past water came out. So these are also paleoclimate reconstruction things that we can do. What happens for the uranium mines is down in here, these are caves. So this is an artificial cave I put in here. And over geologic time, it collapses into what's called a breccia pipe. Or it's a chimney, more or less a broken up rock, this breccia. And it propagates to the surface, and there's a little depression in the surface, and the surface water plays connect the dots. There was a storm in the mid-'80s that wiped out the road to the Grand Canyon, over a 100-year flood. It disappeared in 5 miles underground. And so as water moves up and down these things, what it does is it hits certain units with low oxygen, and uranium in small amounts in the water is precipitated at that spot. And so in the Grand Canyon breccia pipes, it's deposited in the Hermit Shale, the upper Esplanade Formation of the Supai Group, and a little bit in the Coconino here. And so this is a picture of a breccia pipe here. So there's a uranium mine in the Grand Canyon, and I just want to illustrate that now. So here's our perched water system, and here's our shaft coming down into it for uranium mining. And that means that perched water can leak down into the main aquifer that has high uranium in it. It also means you can dry up this perched aquifer system and the little springs that are up high into the perched aquifer. Almost done here. Fingerprinting. This is called an activity ratio here. This is the tritium ratio, and this is a way to fingerprint groundwater. What an activity ratio is, it's a 234, 238 uranium isotope ratio. And this would be 1 here. This is called secular equilibrium. Usually it means you might be near a uranium mine, or there's very, uranium that's been exposed recently. Tritium is more or less age. This means it's very, very old over here. Everything over here means it's probably pretty young. And guess where Horn Creek below Orphan Uranium Mine was? That was right there. Okay? So it's a way to fingerprint, and it's evidence that there might be a connection between uranium mines and springs. So the last science here, this is dye tracing test that the Park Surface did. This is on the North Rim. They're dumping dye into the ground. And this is a rather complicated chart, but here's the Grand Canyon moving through here. This is where they put in the dye here, 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 and different times. They expected it all to come out in springs in the Grand Canyon down here, and some did in one event, but then they had all these unexpected directions in the fractured rock. Some of the dye went over here to a spring over there. Some of it went way over here, tens of miles away in unexpected directions that they never imagined. And I want to point out one little spot here. If you look, you see one dye tracer test went this way, and right next to it, another dye tracer test went that way. Kind of interesting. This, the dye went in a period of months, not years, and We dated this water. That's what lonely hydrologists do, is they date groundwater from when it comes down as rainfall and it comes out in issues and springs. And dating groundwater is a bad term because it implies one date. Usually it's an ensemble of water that takes a long pathway and water that takes a short pathway. So we use average residence time. The average residence time that we measured with tritium dating here was 15 years. So there's a complicated bunch of pathways, some short and quick, like these dyes took, and some very long, and they go in all sorts of different directions. One last problem here. In 1992, I argued before the ADEQ that perched aquifer was vulnerable, that they might have a problem, and they said, no, there's no water in the perched aquifer. Well, a little over a year ago, in December, the mines hit a gusher. And so much water filled up the shaft, they had a surface impoundment. They couldn't hold it in the surface impoundment. This is Canyon Uranium Mine south of the Grand Canyon. They set up these water cannons here, and they shot water into the atmosphere to evaporate it. That is water that contained uranium into the atmosphere to get rid of it because they couldn't hold it all. So what is the future? Will the future be placid or rough? My guess here,
with Mo and Co. ready to high side. The entrance is crucial on this rapid.
I'm actually rowing.
And it looks like he's got it, right? Steve's pushing. There they go. Wow. Woo!
My guess is we're in for more turbulent times. I might add that this is 1983. This is me on my introduction to the Grand Canyon in a kayak. It was a flood year. We hit the height of the flood, and that's Crystal Rapid back behind me there, and that's one rather humbled kayaker going through. If you ever feel highfalutin about yourself, go down a big river in a small boat, and it'll put things in perspective. Thank you for your time. One question. I ran over time a little bit here. Yes. Great question. Yes, has the uranium changed with time? And it fluctuates all over the place. And I believe that it's a function sometimes of rainfall and pulse flow. A lot of people think that travel time is the only thing that's important, but sometimes things can be pulsed out. Imagine a spring as a bucket that goes up 1,000 feet. Let's punch a hole in the bottom of it, and that's a spring. Well, when it rains, more water comes in, you get an immediate response, but the travel time might not be immediate. And so, or if you pump and take water out, the spring immediately will go down. But that doesn't mean the travel time is immediate. And so what we've seen is a real variation in uranium concentrations. They're very, very high. Researchers from Northern Arizona University found higher concentrations. The USGS found slightly lower concentration, but still right at the standard there. And then there have been some times that people have found other concentrations. Sometimes people sample in different places in Horn Creek too, and that affects it as well. That's a great question. We haven't been able to see a climate change signal or any change with time. Thank you very much, everybody.
Thank you. All right, great presentation and great slides. And maybe this is the time that I should mention a lot of people have asked me and asked Sean if they're going to have access to these slides. We post the PowerPoints unless the speakers tell us not to. So I guess that's warning to the speakers. If you don't want your material posted, let us know and we'll accommodate whatever you want to do. But we post that, and we post video of the event, and we post any supplemental materials that someone brings. Like yesterday, Sam Routson brought the management plan for Diamond Valley, so we posted that all as well. If you need any of this stuff quickly, if you need these PowerPoints quickly, just talk to the presenter, because It takes us a while to get all this stuff together, especially the video takes a while to get posted. So, but that's the plan. All right, we are moving now to the Nature Conservancy component of our program. We have two speakers in a row from the Nature Conservancy, and they're both going to talk about issues in the similar geography, the southern Arizona, northern Mexico geography. We'll start with Holly Richter, who's the Arizona Water Projects Director at TNC. If you work on water issues in Arizona, you must, by default, work on groundwater issues. It's such a key part of the equation, and it's a key part of the equation if you're trying to protect the remaining surface water sites. I'll say that when I moved to Arizona in 1990, I had a map, and it's mostly a road map, but it also showed all these creeks, and I was very excited every weekend to hop in my Volkswagen bus and drive out and look at some of these things. And after a weekend or two of doing this, I decided I was thinking, I just apparently don't know how to read a map, because I could not find any of these rivers that were on my map. And then, after a while, you learn there used to be water used to flow there. It doesn't flow there anymore. One of the places where you can find some surface water in Arizona is the Upper San Pedro, magical place. And I won't say any more about it because Holly will, but that is the focus. So Holly?
Oh, here we go. Morning. It's great to be here, and it's a real honor to be in the same room with so many brilliant groundwater thinkers. So we're kind of a rare breed, and it's great to get together. And there's so many different ways I could talk about San Pedro today, but given that I have 20 minutes, I'm going to try to take just kind of a top-line approach to this story, and kind of give you some ideas, try to minimize the specifics about the place, because there's so much detail I could get into, but really try to focus more on what are some key lessons learned, things that could be transferable to other places. And I want to start by thanking Jim Holloway for his presentation this morning, which talked about Arizona water policy in the context of that. He mentioned that the AMA framework was very useful where it's in place, but that rural Arizona is not really supported by the AMA framework. And so those rural basins within the state really have to take a more localized approach, and every one of them has very different needs and very unique water needs for both nature and people. And so I guess what I'd really kind of like you to think about today is that the San Pedro case study is kind of one of those rural basins, probably one of the most complex ones really in Arizona because of some of the designations and history of that place. But this is a story about how a local basin in rural Arizona tried to address this groundwater challenge that we see throughout the arid Southwest. San Pedro River Basin, encircled by what we call Sky Island mountain ranges. It's a long, thin, north-south trending basin. Its headwaters are in Mexico. It's very hard for people to see water flowing up on a map and to believe that actually a river can flow north. But it's true. And so the headwaters in the San Pedro, down here, you can see this map actually shows where the perennial surface water persists with the blue lines. Some of it's not mapped because of access issues. The dry reaches are shown in red. But you can basically see that there's kind of part of the watershed here in Mexico. This is considered kind of the upper San Pedro, which is the area we're going to focus in on. The lower San Pedro down here we won't really be talking about today, but it joins the Gila down here and is obviously part of the Colorado River Basin. So there's some real interesting differences between where that persistent perennial surface water remains and where it doesn't. This is actually a shot of the international border. That's the border fence. And this is still got riparian vegetation, but you'll see there's no surface water there. This is during the driest time of the year. And you can kind of contrast those values, those ecological values, with a reach that does have persistent surface water all year, as shown here. And a lot of people kind of laugh about the size of the San Pedro and that it's a very small river. But frankly, the biodiversity and habitat values of it are off the chart. It provides a migratory pathway for millions of birds north and south in their migrations every year through a very arid landscape. And that's why it's really become such an area of now national and really, I would say, hemispheric importance, because it connects those migratory pathways. The other thing I just have to mention right off the outset about the San Pedro is that it has a fairly natural flood flow regime. And so not every day will it look like this tame little trickling stream. Lots of times we'll see these huge flood flows that are a result of either hurricanes or monsoons. And that's a really important driver of the system as well, and helps to sustain the whole biodiversity of the area. So the San Pedro really had a major turning point in kind of its prominence and its exposure and attention back in 1988, when the Arizona-Idaho Conservation Act passed and established the nation's first riparian national conservation area along the river. And the values were everything from aquatic and wildlife to archaeological, paleontological, scientific, cultural. It's very, it's an amazing resource. And this designation really put it on the charts and got the attention of a lot of people and really started the need for more information about this whole system and how it worked. Not going? Oh, there we go. So this is now just showing you that upper half of the basin. Again, here's the Mexico portion in Sonora. But you'll see here, this is actually that National Riparian Conservation Area that's managed by the Bureau of Land Management. It encompasses about 40 miles of the river just as it enters the country from Mexico. The thing that's really important, we're going to focus on this area of the watershed today in terms of our groundwater management strategies. And the thing that's important in this area is to kind of think about not only this new national asset, new as of '88, but then that it's really next door to another really important national asset, which is Fort Huachuca. And Fort Huachuca is an Army installation that provides the kind of the leading technology on communications and intelligence testing for our nation. And I won't go into why it's located right there, but there are some very important reasons why that location provides just the right context to test some of this communications and really high-tech intelligence type training. So here we have these two national assets, federal assets, right next to each other. And in between, we have communities like Sierra Vista. Sierra Vista's economy, driven a lot by Fort Huachuca. It's a $2 billion economy generated from the fort and its contractors every year. And so here we have a groundwater-dependent basin that has two very important federal players with a rural community in between it, all dependent on the very same limited groundwater resources in an arid climate. And that's kind of the challenge, if you will, that we'll talk about today, and kind of a short history of some of the main events that have occurred over time. The other thing I just want to mention really quickly while I have this map is, so most of the developed groundwater pumping uses are on the west side of the river. This side is relatively undeveloped, and that will be important as we kind of go forward. My button, oh, there we go. So I don't want to be redundant. I know you guys have probably seen and thought about these things in the last couple days a lot, but obviously groundwater, a lot of it, especially in this context, is generated at the higher elevations where we get higher precipitation. The mountain front areas are incredibly important recharge zones, and that water moves very slowly underground towards the lowest point in the valley, which in our case, of course, is San Pedro, and sustains the base flow in the river. So the practical challenge here is that we need to sustain this base flow and the environmental and habitat values that it supports, but we also have to sustain these human demands and uses that could intercept that base flow or that groundwater on its way to the river. And that's just like the simplest kind of statement of the problem that I can give you. This is a USGS illustrations just showing kind of how that gets increasingly challenging over time when you have that kind of a context, because here you can see the natural groundwater flow paths towards the lowest point of the drainage in the river. And then if you start pumping, you start to intercept that flow, and you start to see a cone of depression around the pumping centers forming. Over time, you continue that pumping, and you see the cone increasing, and of course, less delivery, more interception of the groundwater to the river. And then kind of the final stage of this before you lose a flowing river is that you actually get the reversal of those flow paths from the river back into the aquifer and being used by the wells. So we don't want to see this happen in the San Pedro. It's one of the very few last places where it hasn't happened yet. It's what makes this place unique. And yet, how do you stop that? How do you balance the groundwater? So again, this kind of shows from an ecological perspective, you can see there's, and it's very simplified, but just to give kind of the main point that when you have enough groundwater that it sustains surface water in a channel, you have a more diverse riparian community because those plants in streamside forest can access the groundwater more readily. It's a much more complex, much more diverse habitat. When you start to see that groundwater lower and it gets maybe just at about the elevation of the channel or it's right on the fringe between flowing, not flowing, you start to lose some of that diversity, get a simplification of the habitat, and eventually you start to see this, which is, again, the story that's happened over and over again in the desert Southwest, where we see the real loss of the valuable streamside habitats. So again, when people laugh at the San Pedro and just say, oh, it's such a little creek, why care? It's actually this groundwater dependent ecosystem that surrounds it that is the true value and a spectacular value given that it's in this incredibly arid environment and it's linking these migratory pathways. So I just kind of wanted to establish that value so that people don't laugh at my small stream slides. So here's my simplified history of San Pedro and its groundwater conversations over 30 years. And please forgive the fact that this is a very simplified thing that I have left all kinds of details, players, events, and kind of aspects out of. But I want to, again, hit the key points that I think might be most interesting to you in terms of thinking about other places. So I'll start with the 90s. So there was the federal designation in the late 80s, and it changed kind of a lot of things about water and some things it didn't change. And so in the 90s, kind of everything started brewing and bubbling down there because people started to feel like there was this uncertainty. There's, myths started to fly, and people were wondering, what does this mean for my well? What does this mean for our economy? What about Fort Huachuca? How do we balance all this? And it became kind of the height of at least the litigation, particularly aimed at DOD in terms of Section 7 ESA. There's a small plant, Huachuca water umbel, about this big, that's a groundwater dependent species, and that was kind of a big part of a lot of the Section 7 ESA stuff. There was issues about the base realignment and closure process that all of the Army installations go through, and was the fort really a viable installation given the water issues? So all of this stuff started to kind of swirl, and the more it swirled, the more people kind of retreated to their corners, and we started to see a lot of dueling groundwater models. And oh boy, is that ever a waste of time at some level, because, and I say this as a modeler from my previous history, not so much groundwater models, but modeling in general, that we know every model is incorrect. It's just a matter of how much, because they are approximations of reality. They are our best way to represent how systems work, but they can't be perfect because they're models, right? So if you want to have, you can't get anywhere by just trying to pick apart somebody else's model, because you can do that indefinitely. And that was starting to happen, and it wasn't solving any problems in any way. So it was kind of like this binary thing about, will we kill the San Pedro or not? And it was like red light, green light. It was like, there's either a yes or a no answer, and I'll use my model to prove one thing, you use your model to prove another, and it'll be like this binary kind of conversation. So that was the dark ages in the 90s. So the initial awakening is the next chapter of this story. So in 2000, a couple different things happened, which were actually really interesting in this journey. So the first is that ADWR had their Rural Watershed Initiative, which tried to address Arizona's rural groundwater issues through kind of local partnerships and kind of providing seed money and resources to ramp up these partnerships so that the stakeholders and the locals themselves could be part of creating their own solutions. And so this is when the Upper San Pedro Partnership blossomed, and it had 21 different member agencies, local, state, feds, nonprofits like the Nature Conservancy. It was a real mix from all sides of the table. And we decided, you know what? The most important thing we can do is create one model that we all believe in, because we don't want to keep having the dueling models, and that'll go on forever. So the USGS was really identified as that real honest broker for a shared groundwater model and its development. And this was when things got really interesting, because all of a sudden you had like county supervisors in these like technical committee meetings talking about model parameters in great detail, you know, and I mean, it was like everybody kind of jumped in and said, okay, if we're going to do this, I'm all over it, right? And so everybody was all over it, and there was more empirical data that needed to be collected to clarify a few things because people had questions. But that process actually really started to change this whole context in terms of a shared vision, because the model took several years to develop, and we'll talk about that in a minute, but it was the process of developing the model. It was almost like a non-issue once it was done, because people understood enough about what went into it, the assumptions that they all agreed to working with the GS, that they could almost predict what was going to happen by the time the model was done and could do that for them. Very interesting process. But I put a green star by sustainable yield because here's another thing that popped up in the meantime, which was that the 2004 Defense Authorization Act had something in it, thanks to McCain, called Section 321, which actually prescribed how the Section 7 Endangered Species Act applied to Fort Huachuca. And what it really said was, it actually named and acknowledged the Upper San Pedro Partnership as an entity that would create a plan and report on that plan every year through 2011 on how it was going to sustainably manage groundwater as a group together by 2011 and beyond. And so it was really interesting to hear in the previous talk about in California how it's so hard to define sustainable yield, because boy, we had to do it to like respond to this, and it was a very new concept and very hard to do with a diverse group. So I could totally feel your pain in California. But then, so the question kind of changed from this, you know, will future pumping kill the San Pedro or not, to the new question, which was, what no regrets projects or policies could be implemented to reduce that annual deficit and reach sustainable yield by 2011? That was the new question. It was a little bit, I'll say, more productive than maybe the last one. So we had this long discussion about sustainability, groundwater, what does it mean? You know what? We ended up with just adopting the survey's rather general description. And I think this was a really good move, because all it says is that it's, you know, like indefinite amount of time, and it has to deal with environmental, economic, and social consequences, which is completely useless if that's all you use to guide your work. But what we said was, we want specific criteria about what that means to us. And that's when it really got useful. So, so this is what we decided as a group, that the economic needs was, first of all, we need sufficient water. And again, what does that sufficient mean, right? But we, just in a general sense, said for now, sufficient water quantity for human needs, that this was really important. Fort Huachuca remains operational unless for reasons unrelated to water. I mean, these are very specific things, right? And so every kind of rural basin in the state would define these things differently. But unless you have this much specifics about what you need, you can't define the most strategic solution to the problem. So the environmental needs were very much based on the National Conservation Area's kind of mandates and priorities. And so, you know, they have, at the time that the NCA was established, they also had a federal water rights reserve claim kind of hooked onto that. And it has different aspects in it related to flood flows and groundwater. And so, of course, they wanted those things considered in the environmental needs of sustainable yield. So we kind of bundled both sides' specific needs, and this is just an overview. But, you know, we said, this is it. This is what we need to accomplish. So it was getting to that, you know, how do you define success and then figure out how to get there kind of approach. But I did want to just talk a little bit about sustainable yield, because I think there's a lot of confusion about it, and particularly how it relates to safe yield and the difference between the two, because they kind of sound like they're both kind of great things until you dig in a little deeper as to, how they differ in terms of natural systems. So, and this is a very, GS illustration is very simplified. It just makes it look like there's an underground reservoir that's your aquifer, so you all know better. But what it really says is, so no pumping, you know, all the water in the aquifer, the outflows are going to go downstream either as surface water flows or ET, but basically whatever that input arrow is will be the same as the output arrow in a natural system where there's no extraction or withdrawals. Safe yield basically says whatever that input arrow is, we can't pump out more than that. We have to have that in balance. That's safe yield for human water use. But you know what? Just think about it. What does that leave to kind of go down into those outflows for the natural system? Absolutely zero. And I think this is something that, a lot of times we think of safe yield as this good thing, but it's kind of meeting half of the water needs if you're trying to address both natural systems and human. So sustainable yield actually tries to do that fine line balance between the two, and it says whatever those inflows are, you're going to figure out a way to partition the human uses with wells with what's still acceptable in terms of environmental need downstream. And likely, you'll see that this bottom illustration is not the same as the top about the downstream, right? Like we don't have all the flows, we have some of the flows. And what is acceptable in terms of some of the flows is a really critical question. So, but Congress had asked us to do this as part of this Section 321. What's the plan for sustainability? We said we're going to use the GS definition. Here's what's important to us, the criteria about if we're going to meet that sustainable yield goal or not. And so after 321 was in place, we started now using a model that had been finished by 2006. Note that it took 7 years to do this collaborative model building. I just want to say the USGS was like an incredibly patient player in this process, because they didn't just go in a back room and do this. Every part of that was really, there's huge engagement. And that's, I think, was such a good investment of time, because now there's complete buy-in on this tool. But there were some real wake-up calls during kind of the model building process. And so, everyone had been just thinking, okay, once you get into building a model, the first thing you do is, your water balance budget, inflows, outflows, numbers. And so you can sit around and like tweak those little numbers for years, and, the different sides can disagree because they like their number better, and that goes round and round. But then you start to realize that when you start actually playing with the way the model forecasts groundwater changes, that there's something really important to be learned by these tools, and that's the spatial aspect of groundwater management is so key. I mean, it's all space and time, but it's so hard for us to conceptualize this stuff without a model in place. And so here was one of the breakthrough kind of concepts that started to really get traction was, we know we have to kind of, decrease our annual deficit, but we also got to recognize that where we pump or recharge can be even more important than the total annual pumping, at least in the scale of years to decades, okay? Not centuries, not forever, but if we have like a triage thing we're trying to fix in the near future, which I'm going to say is years to decades, this spatial aspect is almost more important than the total water budget numbers. You've got to think about both for long and short term, no doubt. But Stan Leek from the USGS came up with a really kind of helpful tool called a groundwater capture map to reframe kind of this spatial aspect and to get us off of just thinking about a lump sum budget for the whole subwatershed. And this was something that, I mean, it's actually a very complex piece of work, but it was also something that like I could bring to city council and we could talk about, at Sierra Vista with the councilmen. And at its essence, this is how I would talk about this map with them, is that what this actually says is, so these are two different maps, one for 10 years and one for 50 years. So let's just look at the 50-year map on the right. And what it says is that for every 100 gallons that you recharge, that in 50 years, those dark blue areas, the darkest blue areas, 100% of that recharge will help to support stream flow and express itself as stream flow in the river. But if you instead put your recharge facilities in those red areas, maybe less than 10% of that water will even help the San Pedro in 50 years. And they were like, wow, you know what? I think we have some ones in the red area. And it was like we started to get a much more focused and strategic kind of spatial management plan going with a lot of the stakeholders and an increased understanding. Again, this is time and this is space. And these are very hard things to conceptualize without a tool that can do this. So these maps, I just want to say, if there's one thing to kind of think about in terms of prioritization for specific criteria for sustainable yield, here's a great tool to get there, and it really made a big difference for us. So, so we had, all this model development underway, and as we were doing that, people started to say, well, there are some things that we can reduce in terms of pumping. I mean, look at our budget, So back around 2002, actually, it was the annual deficit, I think actually around 2001, was about 13,500 acre feet, which sounds like nothing to you guys in terms of these bigger basins, but it was actually substantial. And really the bigger issue is not even that the annual budget was that, or the annual deficit, I should say, was that, but that there was an 800,000 acre foot cumulative deficit of groundwater in this aquifer since the day that we turned the first pump on. And that was something that people didn't acknowledge the importance and relevance of that. Like, remember I told you our first question here when we started back in the 90s was, is future pumping going to kill the San Pedro? Wow, this realization that we'd already removed 800,000 acre feet and that those impacts hadn't fully reached the river yet, totally not on the radar, totally not on the radar. So getting back to space and time, we weren't thinking about the historical time and the impacts that were already in the ground that had not expressed themselves. And this is like such a common groundwater dilemma, right? But what we were focused on initially during this time period was, okay, well, let's at least get our current use down, right? Let's minimize that to the extent practical. And it did. So if this is kind of a hard, this is a USGS illustration where our deficit is basically it goes from negative 2,000 acre feet to negative 16,000 acre feet. So this is the actual deficit, which actually got smaller, even though the line went up. It went from about, during the period of this partnership, from 13,500 acre feet down to about 4,500 acre feet. And that was a really significant decrease. I mean, it took a lot to get there, right? I mean, this is pretty serious thinking and project implementation in terms of how to reduce demand. And this, of course, then was the projected deficit, which was supposed to only increase in volume, even though the line is going down. So basically, you know, by 2011, which was the end of that reporting period for the Section 321, we made significant progress. Had we eliminated the annual deficit? No. Couldn't figure out a way to get there. Admittedly, could not. But it was very significant progress. So what we were thinking about was demand management. What do we do in terms of demand management? We made this progress while we developed the model. But then we kind of said, wow, can't get there with just reducing demand. That's when this more spatially kind of focused and targeted aspect of aquifer recharge started to really come onto the screen as the next layer of how to move forward. So now I'm calling this last phase the age of implementation. So really, it's this continuing to build on the demand reduction stuff with additional policies and projects. But we do it really collaboratively now, and so we can do it much faster, and we're much more able to actually make substantial progress. And so that key question continues to be, what's that combination of additional things that we need to do to meet the stated criteria for sustainable yield? I'm going to start going faster. This actually shows now a bunch of, actually 6 different near-stream aquifer recharge projects that were located in the best locations according to the groundwater model that everybody believes in to sustain flows within the National Conservation Area. Over here, this is a very interesting data set. This is the surface water every year since '99. So each line is a year showing where the surface water was present if you straightened out basically the river here. And so it shows that year to year, you can see there's breaks in flow in the same places. We call this the wet-dry mapping data. It's actually a citizen science project that's gone on for 20 years now. And that corresponded really well with where we need near-stream aquifer recharge according to the model. So we were kind of triangulating on this next new strategy, which is how do we make sure to really support those flows with recharge? And some of these projects are already online. Others are coming online pending funding. But the cool thing about it is that we looked at the network of sites and how they interact together in terms of sustaining flows, not just one recharge project versus, individually. It was a more systems approach to if this is really our target to sustain flows through here, where do we put these projects, how many, and where? So the model really paid off. Biggest challenge is how do you get source water for recharge? We've had all kinds of studies in the past about import and different kinds of source water. But at the end of the day, we decided it's got to be in basin. It's got to be either treated effluent or urban enhanced runoff. You see a lot of subdivisions like this with these moats around them where we get these really intense precipitation events and the water goes down these concrete moats and gets shot out onto the desert to evaporate. And we can talk, if anyone has questions about what urban enhanced runoff means, it's the kind of the new water, if you will, that's generated from impervious surfaces in the city. It is not the natural flood flow regime, though. And that's something that we've been very careful to try to acknowledge the importance of. I mentioned that at the beginning of the presentation. We want that natural flood flow regime to stay in place, even given that we need source water for aquifer recharge. And just a quick listing of the members and the funding partners for this near stream recharge network. So it's cities, counties, natural resource conservation districts, some of the private landowners, ranchers, the Nature Conservancy, a lot of funding from the Army, different foundations, and the state as well. So it's been a real coalition of bringing funds together to get the work done. But as I mentioned before, there are still some of these projects that are not yet built in terms of infrastructure. We still have major funding needs. So here is just a really interesting kind of difference in how flows would change over time by 2050. If we did none of the near stream recharge on the left, the yellower the color is, that means that basically the base flow changes. Let's see if I can actually read that. So this is during the winter. So this is the base flow basically is 0 is white, and then if it's blue, it increases, and if it's a warm color, it decreases, okay? So the first one shows that basically if you were to do no recharge, that by 2050, you'd see decreases in base flow wherever you see it's yellow. If there's no color, it's basically around the same as it is now. The middle map shows the maximum build out of that recharge network that we've modeled. And it actually shows that even by 2050, you see enhanced base flows given the design of that network. We also asked the question of, if we do all this wonderful recharge in the US, what about the upstream pumping in Mexico? So there are some large copper mines and other groundwater extractions in Mexico upstream of us. We wanted to know if there was reduced pumping in Mexico, would that be really important in terms of sustaining this, or is that maybe even a better way to go than the near stream recharge? Interestingly enough, the model told us that there was very little difference in terms of reducing the Mexico pumping, at least at the 2,000 acre foot per year level, which we thought would be something that could be doable. So we just, the process of looking there are many different scenarios we've looked at. These are just a few to give you a sense. But the reality is we couldn't have done this as a collaborative group unless we had a tool we all believed in, and we brought our different ideas about what the possible alternatives could be. And I'm getting kind of close to the end here. This is just another way to look at the data from the model in terms of the different scenarios. And this actually shows that one of the USGS stream gauges within the National Conservation Area, what would be the base flow changes that would be projected by 2070. And basically it shows that there would be an 82% increase in base flow at this particular gauge at that time as compared to not doing the near stream recharge. So this is really, hopefully, going to be very helpful information in meeting those specific needs that we've defined as a group. Hopefully, this can even be helpful in terms of things that can be done to make sure that the federal water, reserve federal water right, which is now just entering its kind of trial date, actually as part of the HELA adjudication next year, this may be a way to actually enforce whatever quantification comes out of that trial. This might be a good way to make sure that that water is there. And we're hoping that that's something that can be collaboratively done. This is one last way to look at the difference in groundwater levels with and without that recharge project in place. So before we looked, I showed you what's the difference at the stream gauges. I showed you what's the difference spatially in terms of flow. But this tells you spatially in terms of groundwater. Again, which areas, and on this one, actually, anything that's got a color shows an increase in groundwater over time. So this actually shows, because one of the questions was, well, that's great by 2050, but what about 2075? So you can actually see that there's actually still continued improvement in the groundwater levels to 2075 with the near stream recharge underway. And actually, so we tried to estimate the number of riparian acres within the National Conservation Area that would see rising groundwater elevations. And by 2050, it was about 1,500 riparian acres. But by 25, it was almost 3,700 acres. So still an increasing trend in terms of, again, that streamside forest and the groundwater it needs access to. Now, one thing I will say is that there will be a turning point where the near stream recharge can no longer, continue to sustain these flows and improve them. This work has to continue to be paired with the demand management, and we recognize that over the long term, and those are some additional scenarios that we're still fine-tuning. So I just want to, 2 more slides, say that you can't be a lone bird and be successful with groundwater. Collaboration was essential. The GS obviously was that honest broker for a lot of our modeling. The Army provided $8 million for the land acquisition of those near stream recharge locations, which was just phenomenal. The Nature Conservancy and the foundations that we work with provided the funding for a lot of the hydrologic and riparian expertise. The county not only supported the design of these near stream projects, but is taking on their long-term management, which is a huge O&M commitment given kind of the budgets in these rural areas. It's just phenomenal to me. The citizen scientists that map that surface water every year and have created this data record and that really helps to look at where this flow fragmentation is spatially and to also kind of validate the modeling. And the city of Cerro Vista that was one of the first to do near stream recharge with their effluent and now has a groundwater mound that is miles in diameter. And that was really kind of the proof of concept project for this network of projects. And it was not without a lot of, I'll say, kind of contention and issues that they did that project when they did. So this is my closing slide. And this is just getting back to the Arizona thing that, of course, Tombstone, Arizona, OK Corral is in our watershed. So I just wanted to let you know that this was kind of, the Cochise County way has not always been collaboration. And this has been a real turning point. And yet, one of the secrets to making that collaboration work was to kind of keep with the OK Corral theme, and is that you can't take just a shotgun approach to groundwater sustainability and say we're just going to figure out a way to be sustainable in this like vague kind of way. You have to take like a rifle and you have to say this is exactly what it will take for our basin to be sustainable and to accomplish sustainable yield in environmental, social, economic, these specific things, and we then can use the tools to get us to those specific things. And that was, I think, what kept us able to continue this progress. It's still, it's at least it's not a red light, green light, the river's gonna die or it's not fight. It's now this construction project, if you will, that we're adding these different projects, and we're improving the science, and just really grateful that we've had that science to base our work off of. So I will stop there.
Can you ask her a question at lunch?
No, I want to ask her for the group, seriously.
Well,
I asked yes or no.
Sure.
Great presentation. You left out a whole chapter of the failure to form a regional management district.
Oh, yes.
So yes or no, do you think there's still a need for formation of a management district in the area? Yes or no?
Sharon!
Yes, thank you. Yes or no questions we have time for.
Oh, gosh.
She won't answer.
We're doing it without the district. That's basically what we're doing.
Okay.
Oh,
Hard question.
I think it's all right. Okay. All right. Moving on. Again, we're in the Nature Conservancy part of the program here, and we're in the southern Arizona, northern Mexico part of the program, and we have Eloise Kendy, who is a hydrogeologist. I don't think this room has ever had as many hydrogeologists as it's had in the last 2 days. And like Holly, she's focused on keeping rivers flowing. Her focus, again, is similar in the grand scheme of things. It looks like it's the same geographic area, but just it's far enough distant that the issues are, while there's some similarities, there's a lot of differences as well, and you'll get into that, I'm sure. So I don't want to delay us any further, so please.
So I'm on now? No.
You will be.
Okay.
Start talking as you're at.
Oh, my co-authors and I very much appreciate being invited to this conference. We represent a coalition of conservation organizations, or NGOs, that are involved in restoring the Delta. and as well as the binational science team that's operating under minutes 319 and 323, which I'll tell you about shortly. This is the Colorado River. You're all familiar with it. How many of you have ever thought about how all those beautiful canyons in the Colorado River Basin formed? They formed by erosion of sediments that flowed downstream, and where did they all end up? They ended up here in the Colorado River Delta. And the Delta at one time was more than 2 million acres of some of the luscious, most productive wetlands and riparian forests in the world. They had all this water and sediment and nutrients coming down from the Colorado River Basin, and all that desert heat, heating them up and making them productive. And underneath that delta, underneath the surface of the delta is all those layers of sediments which form a binational aquifer, sometimes called the Lower Colorado River Aquifer, sometimes called the Imperial Valley Aquifer in the north and the Mexicali Valley Aquifer in the south. Historically, the Colorado River Delta was, as I said, extremely productive. The picture on the upper left shows how all these driftwood from all the trees, all the forests that was spread as far as the eye could see out to the horizon. And on the upper right were steamboats that used to go as far up as Nevada, carrying supplies for mining and so forth. And they were powered by all those trees that grew in the delta. There was an incredible commercial as well as recreational fishery. That's a totoaba there, which is now an endangered fish. The native Kukapa people used the area, lived there, still do. And importantly, it was a bottleneck on the Pacific Flyway, so that all the birds that came from all the birds that came from up here and were going south, most of them had to go through this little delta here. So it was a really important migratory bird route, and it still is. But as you know, the Colorado River Basin is extensively used by 2 countries and 9 states, provides water supply for 40 million people, many of whom live outside of the basin in places like Los Angeles, Salt Lake City, Arizona, and of course, right here on the Front Range. And so that water never comes back into the basin. It irrigates more than 5 million acres of farmland, produces 4,200 megawatts of hydropower, and as a result, that water and those nutrients no longer reach the delta. This is a hydrograph of annual flow volumes at Yuma, which is right above just in the United States, just north of the Mexican border. And you can see how, under natural conditions, it did fluctuate a lot from year to year, but there was very large annual flows. And as the basin got developed with all those dams and diversions, there was less and less flow over the years. When Hoover Dam was built, that's the largest reservoir in the country, the flows dropped drastically. In 1944, the United States and Mexico negotiated a treaty that assures Mexico at least 1.5 million acres of water per year. And by the time Lake Powell was built, that's how much water they were getting, and that's how much Mexico's getting now. So 1.5 million acres of water compared to what naturally flowed into the delta. As a result, this is what you see. This is how it looks now. We are in Mexico in the air, looking north towards the United States. This is the Colorado River flowing south. And as soon as it hits the Mexico border at Morelos Dam, all the water is diverted into the Mexican irrigation canal system. And what's left of the river is this little trickle that seeps through. As you move further downstream, you can see that the river channel is confined between levees. And the delta actually is still productive, but it's producing crops. It's not producing ecologically valuable wetlands and forests anymore. On the ground, what it looks like is this. So the riparian plants, the groundwater-dependent plants that Holly showed you the nice cross-section slides of, they need to have their roots in the water table. And since and this area down here, the water table has dropped to about 50 feet or more than 50 feet below the land surface. And as a result, it's dry, and there's no riparian forests or wetlands left anymore. That's about a 40-kilometer reach. And then if you go further downstream, the water comes back to the surface because of irrigation return flows. So there's a lot of potential to recreate the healthy riparian habitat. At the moment, a lot of the formerly healthy habitat is taken over by invasive species that are salt tolerant and that don't need to have floods and the natural flow variability to survive. As you move further downstream, you reach the estuary. Now, the estuary is a place where freshwater and saltwater normally mix, and it's, again, one of the most productive habitat types in the world. But in the estuary of the Colorado River, the saltwater comes in, and the freshwater doesn't flush it out, and so it concentrates, and not even salt-tolerant plants can survive there anymore. It's completely sterile. But a coalition of conservation organizations and some forward-looking government agency people from both Mexico and the United States have a vision, and that is to restore the parts of the Colorado River Delta along that riparian and estuarine corridor to create a sequence of patches of viable natural habitat where the birds can migrate and not drop dead of exhaustion along the way, and also restore the economy of the area and restore the river-based communities and have an ecotourism and restoration-based economy. So we've established some demonstration sites, and just to give you a little orientation again here. So the last several slides, this is where Morelos Dam is. And then this is where the water is kind of high. And then reaches 2 and 3 and a little bit of reach 1 are the dry reaches. That's about 40 kilometers where the groundwater is too deep to support groundwater-dependent ecosystems. And then down in reach 4 is where the water levels come back up. And we have, these photographs were taken at the Laguna Grande Restoration Complex. There's also a restoration site at Miguel Alemán, and I'm going to point out ahead of time kilometers 27 and 18, which are irrigation canal spillways, which will come into the story later. And here's the upper estuary. So now I'm going to fast forward and make a very, very long story incredibly short, which is to say in 2012, Minute 319 was signed, and in 2017, Minute 323 was a successor agreement to Minute 319. This was a minute is like, I think of it as an addendum to a treaty that says how that treaty will be implemented. And so these are minutes to the 1944 treaty, which say how water will be shared between the two countries during times of shortage. They allow water to be stored in Lake Mead, and importantly for this presentation, there is an environmental component. And the environmental component provides water to restore the delta. A third of the water is provided by each country, a third is provided by the United States, a third by Mexico, and a third by the NGO coalition. And that, in Minute 319, was divided into a 105,000 acre-foot pulse flow and about a 52,000 acres of base flow. The pulse flow was supposed to emulate a natural flood, but we couldn't call it a flood because it would be a joke because it's so much smaller than a flood, but it was the most we could possibly get. Besides, floods are kind of scary. And then base flows aren't really base flows in the geologic sense. Base flows are just kind of water that's delivered to maintain a healthy ecosystem. So I bet a lot of you know about this. How many of you know about Minute 319? Okay. And so you probably know about you've probably seen pictures like this where water was released from Morelos Dam to great ceremony. In fact, I see some people in the audience here who were in this ceremony and a huge media presence. And you've probably seen pictures like this with all the people, the transformation of, this desolate place where the bridge crosses the dry river channel in San Luis Rio Colorado to this happy place where all the local people are celebrating the return of their namesake river. And you've probably seen pictures like this of before the post flow in the restoration sites and during the post flow and 6 months after when the plants are starting to establish, just like the plan, and a year later and 2.5 years later. Amazing success. And you've probably also heard about how the birds, the water birds and the riparian forest birds increased in diversity and in abundance. And all this is true. This did happen. But what you may not be aware of is this. Although we did publish this is not a secret. It's just not something that we have talked about very much. But about 90% of the water that was released from Morelos did not make it down to the target restoration sites. So this figure shows, it's a schematic water budget, and it goes from upstream at Morelos Dam, downstream to just above the estuary. And the size of the blue here is proportional to the volume of surface water that made it downstream. And then the size of the arrow is proportional to the amount of water that infiltrated into that aquifer where there was this big space that needed to be filled. And it was only because of the fact that the scientists that were advising this realized that it was very likely that we were going to have a lot of water infiltrate into the aquifer, and we might not even have water reach the restoration site targets down here. And so we actually got to get some of the water to not get released at Morelos Dam, but instead bypass that dry reach or part of the dry reach and get delivered by irrigation canals. So that's what this site is, and this site is water that got delivered through the irrigation system downstream. And I should just mention DMS stands for Discharge Measurement Station. So this is pretty amazing. So I was there when the post flow was released, and this is what happened. This is what happened at the front of the water as the river was moving downstream. Can you hear that? There was so much air that was underground, and the water was moving down so fast, and it was displacing the air so quickly that bubbles were rising to the surface, and it was like a jacuzzi. It was really incredible to see. And you may not have seen some of these before and after pictures. This is in the dry reach. This is what the river channel looks like before the post flow, during the post flow, and after the post flow. What's the difference between the before and the after? Anyone? I changed my clothes. There really was no perceivable ecological benefit right here in this 40-kilometer reach where most of the water ended up going. And why is that happening? Why is there a big hole underneath the Colorado River? Well, we heard yesterday morning that in a steady state system, recharge equals discharge. And there's been changes in both recharge and discharge. First of all, and most importantly, all that water that used to come down to the Colorado Delta doesn't anymore. And so what used to be floods that spread all the way across and were sustained for probably months don't happen anymore. There's only 1.5 million acre feet, and most of that is used. So none of that water is, very, very little of that water is recharging anymore. And then on top of that, in 2007 to 2009, the All-American Canal, which Wikipedia says is the largest canal in the world, largest irrigation canal in the world, 23 miles of that were lined. And as a result, about probably an estimated more than 60,000 acre feet of water per year is no longer recharging the aquifer at the canal and flowing south into Mexico. And the Mexicali Valley farmers are very dependent on that water for their irrigation. Third, there was a change in groundwater discharge, which is to say that there are all kinds of groundwater pumping wells. And they're on both sides of the border. I only had a picture of ones on the Mexican side of the border. So as a result of this change in recharge and change in discharge, groundwater levels in the Mexicali Valley are dropping by more than 0.5 meter a year steadily. And that equates to about 375,000 acre feet every year. These are Mexico government statistics. On the binational science team does not have access to any of the data except for the data that we collected ourselves in wells that we installed along the riparian corridor. And here's some hydrographs to show you a little bit about what's happening. The top one, so we're kind of moving downstream from top to bottom. These are representative hydrographs from representative piezometers. And upstream, you can see there's not really much groundwater depletion. That's the area below the Morelos where there's high water table still. And then you can see here in the dry reach how the groundwater is not only dropping, but the rate of drop seems to be accelerating. And then further downstream where the irrigation return flows come in, you can see that the groundwater table is still pretty stable. This map shows the change in NDVI, which is an indication of greenness, which is an indication of evapotranspiration, or ET, just over a 1-year period, 2016 to 2017. And the brown shows the places where there's been the biggest decrease in greenness. So one of the things we learned in yesterday morning's session was that groundwater pumping can capture water from evapotranspiration. Well, we're actually seeing that in inset A and D. Those are probably about the most brown that you see here. And we think that's because the groundwater table, this zone that's being affected by the groundwater dropping, that zone is growing, it's expanding. And as it reaches out to the edges, the plants that used to depend on that groundwater can no longer access it, so they stop evapotranspiring. And you can see it in a change of greenness. You can also see it here. This piezometer, which is, let's see, somewhere around here, it had good steady water table from this starts in 2005, for about almost a decade, and then now we've recently seen it consistently start to drop. And that's where the groundwater dependent plants can no longer reach that groundwater anymore. So this is really a big risk for our restoration program. We're putting in new, we're restoring native groundwater dependent species like cottonwoods and willows, and we're putting them in places that are vulnerable to this change. And we're planning to put them in places that are going to be affected, within the next year or two. So what can we do about that? Well, one thing we can do is just maintain them with irrigation. I mean, that's totally possible. We can maintain all these sites just by irrigating them through the canals. And we actually do. These are all from our restoration sites. And that's really water efficient. You put the water right on the plants. You don't have to fill up a canal, or you don't have to fill up a river channel. You don't lose as much to the aquifer. And you can restore the habitat that way. But there's extremely high water delivery fees. We're already paying hundreds of thousands of dollars per year in delivery fees, and then we also have to pay to monitor and enforce those deliveries. We have to pay to maintain the irrigation infrastructure. So it's a really expensive way to do restoration, and it's not very compelling. The kind of money that it would take to do that, we're not going to be able to attract from donors and from governments if we're not doing stuff like this, if kids aren't able to swim, if we're not restoring the river-based community. So by putting water in the river, in contrast, we get recreation, we can have the social value, it also creates even more water bird habitat because of all that open water area. There's no water delivery fees, but it uses way more water, and it's just short-lived. That water, you know, those pictures of the kids swimming and playing, that was only for like about a month, I think. What? 2 months, maybe. Yeah, it's short-lived because that water eventually infiltrated. So that's under the current conditions. That's under the status quo if the groundwater table keeps dropping. If the groundwater table were to recover, then these in-channel flows would persist for longer, and we would be able to achieve all of these benefits without having to pay these high costs. And at the same time, we'd be able to attract more interest and more funding in order to support the overall program and make it sustainable. So make it, you know, hydrologically sustainable as well as financially sustainable. In order to reach a balance, you need to either increase recharge or decrease discharge, or both. And so these are a few ideas that have been tossed around. I'm not advocating any one or another. They all have, you know, obstacles. But to increase recharge, you know, I have to say that you could increase flow from the north, surface water or groundwater. Physically, that would solve the problem. Maybe we could do some more targeted recharge, like the way Holly was just describing, where we identify places that need to be recharged in order to affect our, you know, in order to sustain our restoration sites. Another thing is that for minute 319 and minute 323, the water that the United States and Mexico provide for the environment comes from conservation projects. Well, these conservation projects often are lining canals. So we have to be really careful that if canals that are lined as part of these conservation projects aren't already really important sources of recharge to the aquifer that we depend on. We also can potentially decrease discharge. Reducing pumping is possible. The Mexican government is currently trying to reduce pumping in the Mexicali Valley by 10 to 15%. They don't have an enforcement mechanism for that, but they are doing it through the watershed councils. It's physically possible to relocate the pumping to places that would have less impact on the river, but it's difficult because unlike surface water, even though there's a really active water market in the Mexicali Valley, groundwater wells are tied to the place, to the land, and they're usually owned by 4 or 5 farmers, so it would have to have all of them agree to move it. It would be complicated. It's possible to change to less thirsty crops, and you know, you could definitely save a little bit of water doing that. Importantly, there's about, I'm guessing about 10% of the water leaves the basin and goes out to coastal cities, as well as Tecate. So Tecate and Ensenada, Tijuana, Rosarita are all getting Colorado River water. You know, what about putting them on desal and reducing their dependence on Colorado River water? It sounds expensive, but you know what they're doing now? They're leasing water from Mexicali farmers and pumping it all the way up and over the mountains. So maybe it's financially feasible. Also, some of that water is being used for industrial, you know, high water using industries. Maybe those industries could use less water, or maybe they could reconsider even having those industries be dependent on Colorado River water. So these are a bunch of things, and I'm sure there's a lot more things that could be talked about, but they're not. And a couple of the obstacles also, another obstacle is that there's no groundwater treaty. I won't say an obstacle, it's a challenge, because every case is addressed on a case-by-case basis by the International Boundary Waters Commission. And also federal, in Mexico, there's federal control of water, whereas in the United States, it's by the states. And all the different jurisdictions on both sides of the border have different limits on groundwater pumping and different ways of enforcing and different ways of measuring or not measuring at all. So there's all this inconsistency that makes it challenging. Water demands are increasing, but very importantly, we lack a common understanding of the binational aquifer dynamics. We don't have a shared model like like Holly was talking about, where everybody gathers around and shares the same assumptions and are able to test any of these different suggestions or scenarios. There is a transboundary aquifer assessment program, which began in 2006, and it involves all these different aquifers, and there's only, and it has highly esteemed researchers from universities and state agencies and federal agencies from both sides of the border that are sharing data and building models and figuring out ways to improve the binational groundwater management for every one of these aquifers except for this one. Look at the timing. This was passed in 2006. That's when the two countries were fighting about the lining of the All-American Canal. And the conversation would have been toxic. You know, there was not going to be an assessment of this aquifer until they could talk about the lining of the All-American Canal, which was something that the two sides vehemently disagreed about. But now we're in a different time. You know, now the two countries are working together to restore habitat and to revive river-based communities and an economy in the Delta. And both countries are supporting these projects financially, and they just support it. They like it. And so maybe this is the time now to start a new conversation about binational management of these aquifers, of this aquifer, and start off on a positive note instead of starting off from something that everybody disagrees about. So I just want to conclude by concluding that riparian health depends on the health of the aquifer. I think you should have gotten that from this whole conference. And with a higher water table in the Delta, we can achieve all of the goals that we are striving to achieve, not just restoring the habitat, but also reviving the community and doing it in a financially and hydrologically sustainable way. But we need a binational approach in order to manage this aquifer because it is binational. And the first logical step is to begin a transboundary aquifer assessment. So again, I hope that because of the restoration that everybody likes and wants to succeed, that we can begin a binational conversation on a positive note. That's it.
I'm going to suggest that if you have questions, catch her at lunch. You're going to hang around for a while?
Yeah.
Good. Because if you learn one thing during the conference is don't get in between the people on their lunch. So lunch time. Thank you. Yes, I don't want to walk around the crowd. You don't want to wear this?